suit up.
Thanks.
Let's go. Yo, Christian, make sure you don't forget your corsage. It's really important. You need to give that to your prom date.
Yeah, no, don't worry. I got you.
Alright, cool.
Alright, Christian, I think we're all ready to go.
Let's get it.
Facts.
Tonight's about to be so lit, about to be picking up our prom dates. It's gonna be a great time.
True.
Alright, let's listen to some Ice Cube.
Alright.
Yo, Christian, do you remember your corsage?
Let me check. No, I got it.
Oh my gosh. Alright, we gotta turn around.
Oh man, Christian, your corsage is right on the counter.
How did I forget it? Now we're ready to go prom.
That's a fact. Let's go.
The scenario involves Michael and Christian driving to prom. Christian forgets his corsage and Michael needs to head back to the house. The distance that was driven away and back to the house, as well as the time taken, was approximated. As you can see, the distance was measured in meters and the time in seconds. The data was written on the data table shown, and the graph drawn represents a position graph. So the first question is, what's a derivative? A derivative is a function or a data's rate of change over time. Because we have a position graph, its first derivative would be a velocity graph, and the second derivative would be an acceleration graph. The actual derivative can be found by making a tangent line to approximate the data, but this is hard because we aren't actually given a function. But we can find the average rate of change by connecting 2 points, any 2 points, to form a line which gives us something called a secant line. To recap, the secant line gives us the average rate of change, which is the slope of the line. It is important to know that a tangent line and a secant line are not the same thing. The tangent line simply touches the graph at one point and gives us the actual derivative. Now we can see that there are 3 secant lines drawn to find the approximate velocity at 40 seconds. The smaller secant line is drawn in between 2 points, the more accurate the approximation will be to its actual velocity. The top secant line shows the approximation that Michael was driving 0.825 meters per second at 40 seconds. The middle shows he was driving 1 meter per second at 40 seconds, and the bottom shows that he was driving 6 meters per second at 40 seconds. The most accurate secant line used is the last one because it's closer in proximity to the slope being found. The next secant line drawn is when the graph decreases. The approximate rate of change from 180 to 170 seconds was negative 2 meters per second. This can be supported by the graph because the direction changes. The derivative of a function can tell us whether the velocity is increasing or decreasing based on the sign of the derivative. Because the graph is increasing from the interval 0 to 160 seconds, the derivative would be positive, and since the graph is decreasing from 160 to 280 seconds, the derivative would be negative. If the derivative were equal to 0, the graph would show constant data or a line. From the graph, we know that there is a maximum at 160 seconds, which means the derivatives changed signs. When the derivative changes sign from positive to negative, this would show a maximum like on the graph, and vice versa.
Christian, don't forget.
Restart. You stuttered.
Christian, make sure you don't forget
Mike, let me. Oh. You do that. If you do that, my suit was really bad.
Oh.
It was really bad. Like it was. I didn't do it very smoothly either. It was really buttery.
It's like mine.
It was more like.
You gotta put the.
Oh, buttery.
Cousin! I hope you enjoyed this presentation. Thank you, and enjoy the rest of Calculus's glory.